Can you hear me? Probably. Okay. Yes, okay, we've reached a comfy stage with the audience now. Nobody's sitting in the aisles anymore, which is quite a good thing. That means I frightened a lot of people off with last week's lecture. Well, I'm going to frighten a lot of you off with this week's lecture, because this is I've decided to bring forward the proof. The proof was going to be in next week's lecture, but the last lecture, when I looked at the amount of material to go in, it seemed to have doubled, and the lecture that was to have been this week was done in a few minutes at the end of last week's, and so anyway, it seemed possible to sort of pull it forward. You know, I'm more nervous about this lecture than I've been about any of the others. I always believe in letting it all hang out. I'm quivering inside. That's because, I don't know why it is, really. First of all, I've been essentially hurried up. I'm not used to working with slides. And I flash a thing up and then it's out, you know, and it would take me a long time to say it, and I don't like just reading off the slide and so on. I'm not used to working with slides. I don't know, there are various other things. But anyway, let me start, I think, by summarizing where we're at. You know, this chalk here reminds me of a lecture I gave in Moscow many years ago. They had pieces of chalk that were square section and fatter than this. And moreover, they also had, in the room that I was lecturing, a cloth blackboard that was just a gigantic thing on rollers, you know, so that you push the button and it went another 10 feet higher. You could see the entire thing on the board. But this chalk didn't take terribly well on the cloth. It was awful. So I suppose it takes well here. So let me say where we were. I'm intending, yes, so as not to get hurried too much, to use the slides as summaries of what I've said at the blackboard, roughly speaking. I don't know how well it'll work. So, what did we have? Well, last week, well, no, maybe not. So far, the story so far. Well, I'm not going to describe the bits that aren't directly relevant. I had a sort of survey of what various philosophers thought about free will in the first lecture. But we had the KS paradox. That stands for Cauchy and Specker. I'll remind you roughly of what that was. I'm supposing that you have been to the previous talks. Anybody who's here, you know, just for the nonce has to sort of take their chances. I defined a certain set of 33 directions through the center of this cube, and here are 9 of them. They're the same as the opposite directions. You're to imagine when I draw a dot here, it connects to the center of the cube. So there's another set of 9 such things up there. I'm only sketching it. And then there are the 12 edges of the cube, but since everything counts the same as its antipodal point, let me just draw one line. I'll draw this green line from this dot to that dot, so you understand how these dots represent lines. The chaos paradox says, on the one hand, it's a rule of quantum mechanics, which we call the spin law, or the 101 law, which says that if ever you have three mutually perpendicular directions, you can ask your particle what its spin is, officially squared component of spin is, in those three directions. I'll draw another one, by the way, while we're here. Oh, no, I won't. It needs another colour. You can ask a particle what its spin is in those three directions, and you always get two ones and a zero. And the Cauchy-Specker paradox is, you'd think the particle, the natural thing to do is to think that the particle responds with what its spin actually is in the direction you ask it. But it turns out that that cannot be, because there isn't a way of labeling these with ones and zeros that satisfies this 101 law. And so a consistent set of answers doesn't exist. And that means, well, I described it roughly as saying that the particle is making up its answers on the fly. In fact, one can't really say that, and or at least we won't be able to say that until the end of this lecture. What we can say is that whatever it answers is not just a function of the direction. There is no function of the direction with this 101 property. Let me make it clear what function means. It's something that for every direction, in this case, assigns a number 1 or 0. Okay, that's the chaos paradox. And then there's relativity, which was the subject of relativity. This, by the way, was lecture 2. Here's lecture 3, which was last week. Relativity and the Finn axiom. And the Finn axiom, Finn stands for finite. It basically says you can't transmit information at more than a finite speed, and that speed is the speed of light. But it's really important to realize that that's not just an arbitrary sort of dogma. The great Einstein didn't just say that, and then everybody's got to believe it from then on. What he really said is that physics is invariant under certain symmetries, and I had a little model for those symmetries last week. If two points are spatially separated, that means they're at such a time that theoretically it would require more than the speed of light to get from one to the other. 2 points of space-time are spatially separated. Then you can regard either of them as happening before the other. A point of space-time is a point of space at a particular time. Space-time doesn't have an overall definition of time. I showed you that if you make your clocks tick when they pass certain hyperbolas instead of straight lines, that's obviously consistent, and yet different people see different events in different orders. But then there was also EPR. This was going to be in lecture 4, but I pulled it back into lecture 3, so I didn't say very much about it. But the EPR, the Einstein-Podolsky-Rosen paradox, or whatever it is, and the twin axiom. And that says that it's possible to put two particles into a really special state. It's actually called the singleton state, and then spatially separate them, so that if you ask them the same questions, they'll give you the same answers. Now, a question is just, what is your component of spin, your squared component of spin in a given direction? That's also, these two properties, the spin and twin axioms, come from quantum mechanics and are therefore mysterious. Everything about quantum mechanics, in my view, is mysterious. Relativity, I understand reasonably well. But these two, although they come from quantum mechanics, have the virtue of being operationally testable. This one isn't operationally testable, but on the other hand, when you take the Finn axiom really follows from the symmetries that physics has, the Lorentzian symmetries, and they have been, observationally verified very much. Okay. Let me try and go over and see what the first slide says here after this one. This geometrical configuration is where all those particular directions came from. Where are we? Okay. So here is the statement of the free will theorem. If each experimenter can freely choose which directions to measure the spin, officially that should be squared component of spin, then the particle's responses are similarly free. Now I'm going to set the stage. We have one experimenter with the experimenter is called big A, and his particle is called little a. And he's on Earth. And therefore he's perhaps a bit better equipped than his colleague on Mars. And he's going to measure, we just discussed the fact that measure is actually a bad word for it. He's going to observe the squared component of spin of particle A in 3 perpendicular directions that I'll call x, y, z. Okay? So let's say A measures, I will use the term observes, little a in 3 perpendicular, that's the standard abbreviation for perpendicular directions, x, y, z. That's the picture on Earth. And now I'm going to waste time by limping all the way over to the far blackboard. And I'll use the clean one, I think. No, I won't, because it's nicer to be able to push it up. And on Mars, we have experimenter big B and particle little b, and experimenter big B measures, observes particle little b in just one direction. Which we'll call W. Okay. So basically they're both going to ask the particle some questions. A is going to ask 3 questions, and we know from the spin axiom that the 3 answers will be 1, 0, and 1 in some order. Why is B just observing his particle in one direction? Well, that's because that's all we needed. That's not a big deal. He could have observed it in 3 perpendicular directions, u, v, and w, and if you want them to perform the same experiment, let him do that, but then only throw the first 2 away. Ignore what the answers were for u and v, and only record the answer for w. Okay. Right, now let's see what my next slide says. By the way, yes. I think this gets said. Okay, what does free mean? Oh, yes. So look, if each experimenter can freely choose which directions, I'm going to suppose that A can freely choose. Well, no. Now I'm going to suppose x, y, and z are one of 40 particular triples. In this configuration here, there are 33 directions. I'm just going to write that. W will be one of, let's say, the 33 directions. And what I mean by that, I mean there are 33 directions, counting antipodal directions as the same. There are 33 directions in here. But there are also, essentially, there are 40 triples of 3 orthogonal directions in there. That's not actually quite true. There are some pairs of orthogonal directions for which we didn't have the third one. Well, we just add it, and then we get 40 triples in there. So this is a voluntary renunciation. I'm going to say, A will choose X, Y, Z to be one of the 40 triples in this slightly extended sense, the Perez configuration. And in case you're wondering what the Perez configuration is, it's the thing mentioned over there. And B similarly chooses one of the directions. And now, what we're going to sort of suppose is it's possible each experimenter has to make a decision. For one of the experimenters, he has to choose one of 40 buttons to press. The other experimenter has to choose one of 33 buttons to press. And I'm supposing they can press whichever they like. That decision as to what button they press is not forced from the beginning of time. I'm supposing free will. It's conceivable that we don't have free will. In this case, this hypothesis is not fulfilled. But if it is, then the particle's responses are free. And what does free mean? Well, it means the same thing for experimenter and particle. The free means that it's not a function of the past history of the universe. And I use function, the mathematical term. You can say it's not determined by the entire past history of the universe. Okay, now I've mentioned the spin axiom. Okay. And I've mentioned the fin axiom. Now, the fin axiom is a little bit contentious because it says there's a finite upper bound to the speed at which any information can be transmitted by any means whatsoever. And we don't know all the means of transmitting information, and I rather suspect we never will. But later on, we'll analyze what we actually use and in some detail, and that's only a very small part of this information. And what it amounts to saying, this min axiom, you won't understand it if I tell it you now, but what it means is essentially that A cannot guess what B's, or cannot determine what B's free will decision is going to be. And B can't determine what A's free will decision is going to be. And the real reason for that is the symmetry of physics. You can choose a coordinate frame in which A's experiment comes before B's. And not only A's experiment, but particle little a's response to the experiment comes before B's experiment completely. And so, it comes before that, so B's still free to choose in that coordinate frame. And so we can't possibly work out what B's going to do. But the situation is symmetrical. There's another coordinate frame in which B's experiment appears before A's. And min makes that very clear. Okay. And now there's EPR twinning, which I already mentioned on the blackboard. Twinned spin 1 particles will give the same answers if asked the same questions. Now, let me just turn this thing off for a moment. Good. Then we're not distracted by that. There seems at first to be something inconsistent about this. Do you remember I told the story of my playing 20 questions with my sisters? And then I was free, really, to invent a new object whenever I wanted to, provided I was clever enough to make it have the same answers as the original object to all the pre-existing questions. Many people see a sort of contradiction between these two. So let me tell you what it is now. If my sisters, who were quite forthright, aggressive girls, locked me and my twin brother in separate rooms and made us promise to give the same answers if asked the same questions, then we couldn't easily change our object, could we? I mean, I begin to sense they're getting near. I change the object, but how do I tell my twin brother? I can't change the object without communicating to him what I'm going to do or something, And there seems to be the same sort of problem with the two separated particles in the EPR thing. These particles promise to give the same answers. It's a law of physics that they will give the same answers if asked the same questions. Okay, but on the other hand, the answers aren't determined ahead of time. That's what the KS paradox shows. Or the answer at any rate doesn't depend just on direction. So doesn't that imply some kind of communication between the two particles? Well, no, it doesn't really. I mean, first of all, communication between particles, what's that? I mean, I can communicate with a person. How can I communicate with a particle? Or how can one particle communicate with another? What does it mean? All we have any right to assert is what's stated in the twin axiom. They will give the same answers. That's a very puzzling thing. I have no idea how they do it. But in case you think... this is often explained in popular expositions of physics. The EPR problem is discussed all over the place. And it's often stated that, A observes his particle, and in, say, direction, whatever this is, and it gives the answer 1. And then immediately we know that if B observes his particle in the same direction, these were supposed to be parallel, it will give the answer 1. But this answer was not determined ahead of time. So people think, the particle little a must communicate with little b to arrange to give it this answer. And you often see the phrase instantaneous. We know instantaneously, maybe, what particle b will give. As soon as we've measured a, we don't know. We can show we don't know what a will be. That's the KS paradox. But as soon as we've measured it, we know what b will be, even though, ahead of time that wasn't determined. That's a statement about our knowledge. That's not a statement about the particle. And the real answer is we don't use that language because there's no meaning to the phrase, no invariant meaning to the phrase transmitting this information instantaneously. There's no concept of simultaneity at large distances. So we must not use that expression. That's all. Because physics does appear to be invariant under the Lorentzian symmetries. And in the Lorentzian symmetries, it's not determined which comes first. Now, what is actually stateable and true is that if and when both experiments have been performed, they'll give the same answer. That's a correlation between two different things, distant things. That correlation is a rather peculiar thing. That correlation can subsist without the answers being determined. Okay? That's, you may find that hard to understand. Everybody found that hard to understand. People are still inventing theories which, run contrary to that. But there can be no justification for saying that anything is instantaneously transmitted, because that's a non-relativistically invariant statement, and physics is relativistically invariant. So one cannot say that, even if one would like to. It's true. You see, here is the thing. It's true now. I know here that if at some later time, which is later, this is later, that if at some later time B observes his particle in this direction, he'll get the same answer as I did. So that were, and if there's some transmission going on, maybe you think. No, but it can't be, because I equally know that if B did his observation yesterday, or 5 minutes ago, then he'd already got this answer. No information can possibly be transmitted in this direction, because it doesn't help if B's experiment was already performed. And similarly, the other way around. This fact that the time order of two events is relative to your coordinate frame stops those statements from being meaningful. But it still is meaningful. So let me say, if B did it, which way around? If B did it 1 minute ago, he got this answer before I did. If B did it 1 minute in the future, he'll get that answer after I did, so to speak. If B did it now, instantaneously with me, he'd get the same answer. Those statements are all slightly illegitimate, because I said if B did it 1 minute ago. Well, with respect to my coordinate system. The true coordinate system is that when both experiments will have been performed, they will have given the same answer. That's meaningful. That's invariant. And no restatement of that involving information transmission is invariant. I'm sorry, that took a long time for me to explain. I want to put this thing on again. Oops. Did it go on? No. Oh, I pressed the F button. Okay. Let's see. So I've already said this. Experiment A measures the spin for particle little a in 3 perpendicular directions, and B measures particle little b in just one direction. Okay, let me carry on. So now, what I'm going to prove is what I announced before. There is no function of the past of a given particle which tells it what to do. There can be no such functions. And so we're going to suppose that there is such a function. Not quite sure how to state this function. Let me come in and sort of describe the past light cone here, and then look at all the universe, the parts of space-time that are in the past of this particle. And now what I'm going to do is I'm going to take... Oh, that was meant to be a Z. What I'm going to do is consider all the information that's in this chunk of the universe. Well, no, I'm not even going to do that. No, I'm sorry. I'm going to take an arbitrary... That's what I used to do. I'm going to take an arbitrary coordinate system. So time is increasing. This is just A's local time. It doesn't mean anything absolutely, just A's local time. Time is increasing in that direction. And then I'm going to look at this backward half space and let alpha be all the information in there. Okay. I'll do a similar thing for B in the end. Now, what do we mean? This information you can think of as a whole lot of noughts and ones. You can code information in bits. I'm just going to take a typical bit here, but we're going to say the same thing. So I'm going to suppose that particle little a's response is a function. And I'm actually going to call it little a, because it's convenient to think it's what little a will answer. So it's accidentally given the same name as particle little a. And we can suppose it's a function of x, y, z. That's reasonable to suppose it's a function of x, y, z, and of alpha. This past information here. Actually, I want to move that right parenthesis a little bit. Now, is it a function of w? You know, does it vary with w? Well, I don't know. But, you know, in mathematics, we can take, say, the number 1 to be a function of x. There's a function of x called the constant function. It takes the value 1. So whether this function varies with w or not, this is a clever trick, rather subtle. Whether it varies with w or not, I can throw w in as a new argument, which might be, there might be no dependence on it. But at any rate, that allows me certain things. Okay, and now the question that arises now is, can an information bit alpha vary with x, y, z, and w? You know, well, if it does, so to speak, I'll call it bad. And if it doesn't, I'll call it good. And we have, by the way, over here, a very similar picture. Here is, oh, yes, it's quite important that B's chosen coordinate frame in which the behavior is functional might not be the same as A's. So these are slanting in different directions. B's time, which I suppose I might call T prime, increases in a different way to A's. But we're going to do the same thing. The B's response is going to be B of, well, it might not vary with X, Y, and Z. It probably does vary with W. But even if it doesn't vary with X, Y, and Z, I can throw them in as new arguments. And now we have beta, where beta. So beta is all the information in the past half of the universe. I raised this bugbear of the possibility of information that varies. Well, if it does, call it gamma and reserve alpha for this kind. So what I'm going to do now is I'm going to split these information bits into two types. The alpha will now mean only the ones that are good, that don't vary with X, Y, and Z and W. And then I'm going to do a similar thing. Let me limp over there with beta. I split it into two types, good and bad, so to speak. Well, can it vary? Well, if so, here's what to do. I'll continue this blackboard over here. Replace gamma by gamma 1, gamma 2 to gamma 1320. Well, let me tell you what 1320 is. That's 33, no, it's 40 times 33, which are the values on, or let's say its values on our 40 times 33 quadruples. Remember, XYZ is chosen from one of 40 possibilities, and W is chosen from one of 33. So altogether, there are at most that number of possibilities. Now, these don't vary. These are constants. This is the value it would have for the first quadruple. Whether it's going to be asked the first quadruple or not is unimportant. It would have this value because we're supposing it's functional. We can say, in the presence of the function, we can say what it would have been if we'd done something else. That's what you can't do in real life. Since we are supposing that it's given by a function, we can say what it would have been if we had any one of these. And now, its value on the first quadruple is a constant. It doesn't vary with the quadruple. Even if we're asking about the 77th quadruple, gamma 1 means the value on the first quadruple. These are good bits, good information bits, so they're among the alpha. Okay, that's a clever trick, a rather dirty trick, though I say it myself, but a clever trick. So that means we can replace any bad information bit by a finite number of good information bits, and they're already there. This was supposed to be all the good information bits. And over there, when I can bother to go there, we'll do a similar thing. I think I'll do it now. Wait a moment. Okay, so we've named all of those. I'll leave that up a bit while I go over here so you can read it. So now, beta doesn't vary with X, Y, Z, and W. Now, what I want to do is choose an instant. And instant does mean something here. It means in the sense of this time. Choose an instant when B is just about to pick, say. I've already used the word choose in this sentence, to pick a W. Snap! I mean, we've now got, let's call it beta naught equals state of the past. At this time. What I think of doing is taking out my old Kodak camera or something, or my Brownie box camera, and snapping the universe fixed at that particular time. Well, it's not at that time, it's the state of the past at that time. So here it is now. And I'm going to just concentrate on this. Now, these betas are independent of x, y, z, and w. Okay? So this same beta naught here, this same past, could work for any x, y, z, and w. But I'm going to sort of remark that beta naught, how can I say it? That this is actually independent of x, y, z. And it's independent of x, y, z because in a suitable frame, x, y, z are yet to be determined. I will come back and say something about that in a moment. Let me see what was said on the slides about that. Okay, there's a value of beta, say beta naught, for which that thing is defined. I suppose I should give you time to read it. Well, now let me... have I given you time enough to read it? I will count 15 seconds from now. I'm really quite excited to see what's next, because I've forgotten what's next. Well, I can't wait 15 seconds. That was 10. Yes, that reminds me. When I was first lecturing to students in Cambridge, I got a bit disturbed by the fact that they wouldn't ask questions. And so I instituted this thing whereby I said, I'm going to wait for 1 minute every quarter of an hour, or until somebody asks a question. I then learned how long 1 minute was. It's a tremendously long time. And you know, those students did not say a thing during that minute. So, you know, at the half-hour point, I did the same thing, and then I think somebody did hesitantly raise their hand. Okay. So I've already said that. Oh, yes, the important thing is now, we're going to do an experiment. B is going to do an experiment after he chooses W. This experiment is going to take a very short time. He's going to choose W. Sorry, not after the instant I mentioned over there. He's going to choose W. That's a free will decision. That the physiologist tells us that takes about 1/10 of a second. And then the equipment has to be reorganized, but that takes very, very small time. So we'll still call this 1/10 of a second. Okay, but anyway, here's the same beta naught working. Here's B's response. Okay. Oh, I'm sorry. No, I went back to the previous thing. Now, it can't depend on X, Y, Z. That's because it's got to give... Yes, it's not explained terribly well here. It's got to give the same answer as A's experiment if W is among the X, Y, Z. But there's some frames in which X, Y, Z are only chosen after B's response. So it's a function only of the direction. So I think I haven't explained that terribly well, but I'm going to proceed onward. This thing can't depend on X, Y, Z. It was always rather implausible that they did, because X, Y, Z are being chosen over on Earth. And by the way, Earth and Mars are 5 light minutes apart. We'll suppose that they're doing the experiment within 1 minute of each other in some universal frame. It doesn't very much matter what that frame is. So that definitely they're doing. Now, you see, let's look at this. This is fantastic. Now, this function, which is, well, let's say, let me, this is independent, and so is now a function just of W. beta naught is a constant. Beta naught is the state of the universe, or the state of the past of the universe, at some point when B is about to choose a certain direction. But now we've reduced, so that's a constant. X, Y, Z, it doesn't depend on. It doesn't vary with, so this is just a function of W. That's amazing. Now, what did we prove? There wasn't a function just of direction which satisfied the 101 law. So let's go and see why we've got a contradiction now. Okay, so let's see what happens here. There's a similarly to be said, namely, this is similarly well, we can choose an alpha naught when A is just about, so let's say similarly, let's say specialize alpha naught to be at an instant when, in A's time frame, when A is just about to choose X, Y, Z. And then let's remark that this cannot depend on W, for the sort of mirror image reason why that couldn't depend on X, Y, Z. And then let's say, I'll continue on to this blackboard. Let me say, and conclude that A's response but what is A's response? A's response is a triple. So let me say that, which is one of the triples naught, 1, 1, 1, naught, 1, 1, 1, naught. That's by spin. It's one of the triples that is, well, let's say has the form. So it's a triple. I'm going to call its first element A1 of X, Y, Z. I'm going to suppress, well, maybe I won't, A2 of X, Y, Z, alpha naught, and A3 of X, Y, Z, alpha naught. Now, a function just of X, Y, Z. This is the same kind of thing as happened over there, except that now both the arguments and the values of this are a triple. Okay? This is 1, this is 0, this is 1, say. Or it could be 0, 1, 1 or 1, 1, 0. But notice it depends on all three things. I mean, the first component of this doesn't just depend on X. It might depend on Y and Z as well. That's how we use the twin axiom. So let me sort of summarize what we've been doing. We allowed these responses to be functions of all four directions and the past history of the universe with respect to the appropriate frame. And now that's an awful lot of information, a tremendous amount of information. And the fight has been to reduce the amount of information. Now, we reduce some of it by just specializing to an instant when the experiment is about to be performed. So we take this snapshot of the universe, of the past history of the universe at that time. And we reduce some more by observing that this thing cannot depend on x, y, z, and that one cannot depend on w. So the only variable left in the function over here is direction. So that's a function of one single direction. And this is, so to speak, a free functions of three directions. But now we have the following. I suppose I can flip it. You see, if w should happen to equal x, let me write that here, but if w should happen to equal x, well, now it's perfectly possible that w might be x, because big B is perfectly free to choose w, okay? And he's only choosing from one of 33 possibilities. Similarly, A is choosing from one of 40. It's perfectly possible that w might be the same thing as x. Okay, so that can happen. Then we get that b naught of w, which is the same thing as x, as b naught of x, must be a1 of x, y, z. I'll rub out the dependence on alpha naught. Alpha naught's fixed. So we don't have to think about it anymore. And if w equals y, I see that this is written on the slide, and I see that I'm coming close up to time, so I will just refer you to the slide. So we see that A's response is actually that thing, okay? So that is given by a certain function of direction. And the response to any triple of directions is the corresponding triple of values of that function. So, you know, we know that A's response is one of the triples with two ones and a zero. And so B naught of W is a 101 function. Okay, but what did we prove in the first lecture? There isn't a 101 function. There just isn't, folks. That cannot happen. So even though this thing was allowed to depend... Oh, my. Somebody's telephoning me. Oh, I can walk over there, can't I? Some kind of telemarketer. So even though this function, you know, apparently initially depended on all sorts of fantastic information, we can recover from it by various dodges. We can throw away this information. We can observe that it doesn't depend on that information. We can specialize the other information. We can finally produce a 101 function, but we can't do that. So all of this nonsense is just nonsense. The behavior cannot be functional. It can't depend even on all this massive information. We've disproved this functional hypothesis. And that, of course, proves the free will theorem. Well, do you remember I said I was going to ignore the difference between the time one chose beta naught and B's response? It's about 1/10 of a second. So let me start imagining now what happens, what might happen that is influenced by the difference between these things. Well, here it is. Here, this experiment was supposed to be performed on Mars. Okay, Mars. And the experiment is somewhere around here. And now it's conceivable that between this instant which I defined beta naught in terms of, and little b's, the particle little b's response, there's about 1/10 of a second there. It's conceivable that some new information bit arrived. Ah, okay. Well, take a sphere of radius 20,000 miles. That new information bit must have started somewhere in that sphere, because 20,000 miles is about the distance that light can travel in a tenth of a second. That's quite a lot bigger than Mars. Mars is between 2,000 and 3,000 miles across. And this is radius 20,000 miles. Still, this is, let's measure it in a different way. This is 1/10 of a second. And then it looks quite a small circle, okay? And here are some new information bits, frantically trying to reach particle little b so that it can depend on them. This is the difference between the information that was available at the time we chose beta naught and the information that was available when particle b responded. Now I'm going to draw the same picture here. Well, the Earth is rather bigger than Mars, so here it is. But this is really centered on wherever the experiment is being performed. We might as well suppose it's being performed there. And again, there are information bits flying in, hurriedly trying to inform the particle of the hot news, so to speak. So let's think of each information bit. If it's a function of earlier information, then that just reduces to the previous case, so to speak. We might as well used it. And otherwise, the universe, the first information bit that isn't a function of earlier information is a free decision of the universe within a tenth of a second, in this case of particle B. Because, by definition, it's not a function of what was earlier. That means it's free. Okay? So what we get is that the response of particle B, how can I say it? It's either governed by some new particle, recently arrived particle, not particle, information bit really, carried by a particle maybe, but that information wasn't there anywhere in the universe before that bit arrived, and so that bits are free. So what we conclude, well, let me proceed to the next slide, since so here we are. We've proved that the universe makes a free decision. Really, perhaps I should have said near at least one of the two particles. Now, we don't normally say that. You do an experiment on a particle and some answer arrives. You think you've measured something about the particle, not something about the universe. It's really a question of words. What we've shown is, well, either the particles, or if you like, the universe in the neighborhood of the two particles makes a free decision. But that free decision is located inside those two spheres. So it's a joint decision of the two particles. And in our paper we call that a semi-free decision. It's rather funny. They're related to each other, and we don't understand that correlation, but we do understand that simple explanations of it won't work. Okay, this is not to be explained in terms of the past history of the universe. Okay, what did we use of Finn? Well, it turns out we didn't use arbitrary information. We only used the fact that B's choice of one of 33 directions cannot be used by particle little a. Particle little a's response does not vary with B's choice, experimenter B's choice. And similarly, particle little b's response cannot vary with A's choice. Well, that is partly, the reason why that's true is because they're separated by a large distance and one could appear before the other. And the other reason is that the experimenters are free to choose. So that combines some aspects of free will with some aspects, a very small use of the Finn axiom. Okay, this concerns a little model for physics, which obviously I'll have to postpone till next time. So let me sort of stop there, but I want to sort of add a final sentence. This seems to be the way the world works. You know, whether we understand it or not doesn't matter. You know, this is not a function. Well, at least if we have free will, so do the particles. It's not a, you know, that's not an arguable matter. This proof really concludes this. But you may be worried. Are these axioms actually consistent? You know, at first sight, maybe the fact that the two particles give an answer does involve superluminal, that is super fast information transmission. Well, no, it doesn't. We can give a simple little model to show that the axioms are consistent. That was what was just coming next. It's what we call a Janus universe. But the trouble is, the Janus universe does not have the symmetry of the universe. In the Janus universe, you choose a notion of time. Janus chooses a notion of time and does things in the order of that kind of time. So Janus's way of operating the model is not Lorentz invariant. Okay? But what the model does is Lorentz invariant. So Janus's explanation can't be the explanation, because there's another explanation that's equally good, reverse the time order. It's a subtle point, and I'm going to discuss a lot of subtle points next time. Okay.